So we are ready to start with our first session, bioprocessing and biomanufacturing using biomass feedstocks. And first speaker in the session represents Estonian University of Life Sciences, and his talk will focus on ways of sustainable valorization of lignin into biofuels and value-added products. Please welcome Professor of Biosystem Engineering, Timo Kikas.
Hello, everyone. It's a pleasure to be here today, and thank you, Kaspar, for inviting me. It's also, I think, very good to speak as a first speaker, because then I can actually give you a lot of background, and it's still going to be new for everyone, while everyone else during the day is just going to repeat my talk, basically. So I'm going to talk mainly about lignin and how to valorize it sustainably into value-added products. So at the moment, the normal or common kind of a valorization path is that you take your lignocellulosic biomass and you use some kind of a processes to valorize it, and then you end up with a cellulose-based value-added products, while lignin is just basically burned for heat and energy production, which of course is not really very high-value product. So, but at the same time, lignin is one of the most abundant resource, or is the most abundant resource of bioaromatics. And from the chemical point of view, aromatics is much more interesting than sugars. And cellulose and hemicellulose basically are sugars. So for me as a chemist, lignin looks much more kind of a valuable product than any of those sugars that are available in the biomass. The problem, of course, being that biomass itself is normally pretty tightly packed, so it's not very easy to really get out of this anything, including cellulose, of course, but lignin especially, because it requires very specific kind of tools to get it out of the biomass. So in our approach, we want to actually go on the lignin first path. Instead of focusing on cellulose, we're looking how to get first the lignin out so that cellulose and hemicellulose maybe will still stay in the biomass or solid part, and then can still be valorized later, while lignin can be taken out so that it can turn it into a valuable product. In principle, there are a whole range of potential pathways and valuable products that can be produced from the lignin, but most of them are still at the rather low TRL. So it's not really ready for any kind of industrial production. But at the same time, market is already there. So there are many things, well, of course, very general things like fuels, BTX, polymers, fibers that are already have the market and have very big markets and are just waiting for bio-based products to come into this market more readily. At the moment, it's not really very high percentage that is bio-based in these markets. And more specifically, looking at the lignin kind of markets, then there is also some very specific products and high-value products that can be made out of those lignin and that can be separated from the biomass. So at the moment, lignin extraction mostly is done by either, or can be kind of categorized into three different options: sulfur processes, sulfur-free processes. Most of the sulfur-free processes are based on either alkaline or some organic solvents. And then there are other processes like pyrolysis, milled wood lignin, hydrolysis lignin. The problem with those is that they normally employ very harsh chemicals. And the cellulose, or the lignin that comes out of this, has cellulose and hemicellulose contaminants attached to it. So it's not really very pure lignin, and which also kind of limits how it can be used later on. And of course, it's also altering the molecular structure if you compare to the native lignin. So in order to get better results and avoid those problems, then we are looking at today's new and greener solutions to this, like ionic liquids and deep eutectic solvents. We are specifically looking at ionic liquid separation, and ionic liquids by itself is a liquid salt. So it's a salt that is liquid at room temperature. Basically, what it means is it has an anion and it has a cation. And as the number of anions and cations is very, very big, it means also that combinations of those anions and cations is huge. So which gives us a possibility to actually design those solvents. So doing some simple modeling and computer chemistry, you can actually predict what kind of properties this ionic liquid might have if you synthesize it. So you can already, before synthesis, kind of try to nudge this solvent towards what you want it to do. Another thing about salts, a good thing about salts is, of course, they're not flammable. They don't have any vapor pressure, which means that you can heat them easily and nothing really happens. So anything else that is inside there will come out while they still stay intact. And this makes actually also rather easy to reuse those ionic liquids, because it's basically quite simple to get anything else out of that solvent. And in our case, one other important point is that it has, as a salt, it has anions, cations, meaning it has charged entities, which makes it also electrochemically very good kind of environment. So if you have a water solution, this is always limited. Your electrochemical window is where you can work is always limited to the oxygen and hydrogen evolution. So basically, if you start degrading water in either one or the other direction, then you already cannot really do any electrochemistry there. While in salts, the window is much wider, so you can also do different kind of electrochemistry there. Okay, and we are specifically looking at the protic ionic liquids because it has a proton, which will help also in cleaving the bonds, some specific bonds in the lignin structure. And this is what we wanted to do. Also, proteoionic liquids are less toxic, and they are easily synthesized. They are actually from natural, mostly natural ions, like ammonium, phosphonium, sulfonium, which are also available in the nature. They have higher recyclability and, as I said, electrochemical window as well. So just to recap what it is happening right now, and we want to avoid basically this part or this part and use ionic liquids and get to the high value products instead. So if you look at the biomass, then, yeah, as I said, it has a very tight structure. So in the plant cell walls, you have cellulose fibrils, then you have around them hemicellulose, and as a glue, you have a kind of a lignin entities in there. And our aim was to synthesize our proteoionic liquid. In this case, it was ammonium-based proteoionic liquid. We actually tried several ones. This one was one of the best, not the only one. There are others, but I'm just using this as an example. Then we investigated the applicability for fractionation and try to optimize the process parameters and characterize the lignin that we extracted. So, process. First, we use ionic liquid with a biomass, raw biomass. Then we use ethanol to separate the liquid solid parts, while the liquid part then goes into the lignin separation, where we use water as an anti-solvent and separate the lignin itself, wash it, and then regenerate the ionic liquids for this process. So we did a whole range of experiments with the different conditions, looking at incubation time, temperature, and also the loading ratio. So, and these are the results that we got. Looking at the incubation time, the 3-hour incubation was the best option, even though in principle you might get a little bit more lignin out when you're using longer times, then you also start losing cellulose, which is not the point. So we actually want to avoid losing cellulose as much as possible. Then from the temperature point of view, the 180 degrees seem to be optimum. And again, little more might be taken out if you're using maybe higher temperatures, but again, you start losing cellulose, which for us would be actually negative. And then the loading ratio, of course, logically, the lower the loading ratio, the more effective the process itself is going to be. However, if you are actually trying to produce something, so on industrial scale, then loading ratio is one of the main points that you want to maximize, because if you are doing your work in very dilute solutions, it also means that you need huge volumes for the production. And again, any industrialist probably will agree that this is something that you want to avoid, because this also means that you need to transport those huge volumes from one place to another. Okay, so this is the results that we got, and in principle, we managed to keep most of our cellulose and got more than half of the lignin out at the same time. So lignin recovery in the end was 56%, while the cellulose content stayed at 93, which means that we only lost minute amounts of cellulose in the process. So we did also some characterization. First, and one of the more simple ones is just visually looking at the cells after the treatment. And as you can see, the smooth surfaces that are present in the biomass itself are actually all gone from this side where you have the treated biomass. So then we also looked at the FTIR spectrum, and the black line here is a Kraft lignin, and the red line is our lignin. And a few important points here is that you have much bigger amount of CH stretching, and also that you have here carbonyl stretching that is not present in the Kraft lignin at all. And then we did also some thermographic analysis. As you can see, the degradation all happens above or below 450 degrees, and the turning point here is actually 263 maximum lignin degradation, while for the Kraft lignin this is about 350. So it actually also degrades at much lower temperatures, which also already kind of shows that we're dealing with a smaller molecule than and more kind of a chemically active molecule than in the Kraft lignin. We looked at the size dispersion also, and as you can see again, the comparison is with the Kraft lignin. The black is Kraft lignin, and the red is our extracted lignin. And as you can see, the upper part of the molecular weight is practically missing from our lignin. So most of our lignin is actually relatively smaller molecular weight. And also the polydispersity index is only half of that of Kraft lignin. Then we also did some NMR spectrum to see what kind of molecules or fragments we're dealing with. Here you can see just like a general kind of a range of molecules that are available there. From here, one thing to look at is that beta O4 bonding is actually completely gone there. And this is the bond that we aim to cleave, because this is one of the most prevalent bondings in the lignin. So if you cleave that, you are most likely to get most of the lignin also out of your system. So if you look at here, then you have all kinds of different bonding, but not beta O4. So basically all the beta O4 bonds were cleaved as we hoped to. The other number to look at is this number here, which is very close to 0. And this actually shows that this lignin does not have practically any kind of a polysaccharide linkages, which means that there is no cellulose or hemicellulose residues in the lignin. So it's a pure lignin without any sugar contaminants. So we did prepare cost-effective, not very viscous and non-corrosive ammonium-based BIL, and were able to recover from the biomass about 56% of lignin. We did see the removal of lignin both visually and also chemically. In the chemical analysis, we did see that the beta-O4 linkages were actually cleaved, and we also did analysis using TGA and GPC analysis. So these are the kind of valorization processes that are used at the moment. And the main kind of products that they are aimed towards are aromatic monomers, formaldehyde, phenolformaldehyde resins, and aldehydes and acids. And we would like to add the ionic liquid separated lignin with the electrolysis as a valorization step also. So that would give basically a completely new line in both the phenolformaldehyde resin and aromatic aldehyde acids production chain. So this is the project that has been or is funding our research at the moment. And the aim here is to go actually using ionic liquid in the IL directly to electrochemically valorize. And here is a whole range of products that we can go for using different potential, electrode potentials. But it can be also separated and go for nanofunctional biomaterials or some packaging or coatings materials. And of course, we still have the cellulose part that can be used for basically the same products that they are used at the moment. So we're still working on the in silico interaction studies, and also looking at the enzymatic depolymerization of ionosoluble lignin, because enzymes are very effective in doing things at very low temperatures with very low energy input, and also still characterizing the depolymerized lignin. We also have a ongoing collaboration with the French INRA and hope to get an access to their synchrotron facility Soleil to actually see in situ depolymerization of the lignin as well. And yeah, so funding team, we have actually, this is not correct anymore. He's not postdoc anymore. He's actually now senior researcher. Sabaratinam Shanmugam Sharib, our student, Margareta, another student who is going to graduate this year. And also we have a collaboration with the German Saarland University from Germany. Okay, thank you very much.
Okay, now we have time only for one quick question.
Thank you. Peter from Bioeconomy. This is not my area of expertise by any measure, but the word on the street has been that ionic liquids are expensive. So does this expensiveness stem from the production of the ionic liquids or the associated costs that you those steps that you have to incorporate if you are using ionic liquids?
Well, yes, but there is a difference. Ionic liquids that you are most likely talking about are synthetic ionic liquids and mostly probably non-protic, like imidazolium-based ionic liquids, which are more expensive because they are also more expensive to synthesize. Our ionic liquids, actually, as I said, are based on very simple ions like ammonium, lactate. So those are all natural kind of ions that are easily available from different processes.
Yeah, that was supposed to be my follow-up question, that when you say that your process is cost efficient, whether it's actually linked to the production of your cost efficient ionic liquids or the simplification of the technical procedure, but I guess I got my answer already. Thank you.
Yeah.
Okay, thank you. Unfortunately, we don't have more time for questions. Thank you very much, Timo.